Hello everyone, welcome to the 5th lecture of our Introduction to CFD course. In this lecture we're going to be working with a blunt body this time around. So the problem for today is this one. So our blunt body is basically would be the silhouette of a vehicle, okay? And we're gonna have air coming in from this side at 15 meters per second. We have a length of 5.2 meters and a height of 1.44. Okay, one of the interesting things that we will learn in this problem is that if you take a look at our geometry here and you slice a plane in this direction, you can see that both sides are the same, right? They are symmetric. So this time around we're going to be using some facilitating tools that will allow us to simulate only half of the geometry, and therefore we're going to need only half of the mesh, which will make the computational process much quicker. And this is something that you can use when you have a symmetric problem. Okay, we're also gonna see another simplification that we're gonna use, which is the free slip condition in some walls of the geometry to simulate the external flow. Okay, we're also going to use a different turbulence model this time around. Instead of the chi epsilon, we're going to use the shear stress transport, because it captures the flow close to the walls more accurately. And we're gonna use also the intensity and length scale turbulence, which is gonna be, I believe, the edge, right here. The edge length scale is gonna be 0.1, because it's, remember, 10 times smaller than our length scale. All right, so let's begin. This is the file that you're gonna receive in email. So all you need to do is extract the file right here. Always make sure that you have the mesh file, okay? Because without it, you cannot open the geometry in CFX. And let's open CFX. Here we go. Now, always remember, choose the proper working directory. Okay, so now that I've chosen the one that I'm going to use, we can start CFX Pre. All right, let's wait for it to open. Let's create a new general case. So remember, you can click this blank sheet, or you can go to File, New Case, and choose General. All right. Now let's import our geometry, our mesh. Sorry. So let's go File, Import Mesh. Because the working directory is already set properly, it's already here, so I can choose it much quicker. And here we go. This is our domain. Okay, you can see this big rectangle here is where the vehicle is immersed, so it will be sort of where the wind is gonna come from. Okay, and this little geometry right here is the vehicle itself, and you can kind of tell already that it's only half of the geometry, right? You can see that it's very narrow, so it cannot be the full vehicle. And this is where we're gonna use what we call the symmetry condition. Okay, so basically the flow of air in the domain is expected to be turbulent. So the shear stress transport, or the SST model for short, will, with automatic walk function, can be used and will be used because it is highly accurate in predicting flow separation. Okay, so to take advantage of the SST model, the boundary layer should be resolved with at least 10 mesh nodes, so the boundary layer near the walls should have at least 10 nodes. And in order to reduce computational time, the mesh in this tutorial, in this problem, will be a little bit more coarser, okay? So we don't have a very fine mesh, because then it would take a long time, especially using the SST model, because it's a more accurate and it takes more time than the chi-epsilon model, okay? So let's create a domain, okay? So we go here, domain, and we're gonna name it blunt body, okay? Now the basic settings for this domain are the location is b1.p3, okay? Make sure you have fluid 1 selected, and make sure that the fluid is air at 25 Celsius, and our reference pressure is 1 atm. All right. Now go to the fluid models tab. We're not gonna be dealing with, we're gonna be messing around with thermal energy or heat transfer, so we can select none here. And like I said, the model is no longer gonna be chi-epsilon. The model is gonna be the shear stress transport, okay? Remember, if you don't see shear stress transport in your outline tree, you can click the ellipses and you can see all the turbulence models that CFX has to offer, okay? But select shear stress transport. Right? Now, click OK. Now, this time around, we're going to create what we call composite regions, okay? An imported mesh may contain many 2D regions, but for the purpose of creating boundary conditions, it can sometimes be useful to group several 2D regions together and apply a single boundary to the composite 2D region, okay? In this case, we're going to create a union between two regions, which both require free slip one boundary, okay? So you can go here in Insert, and you can go to Regions and select Composite Region, okay? The name we're gonna set is gonna be Free Walls, okay? In the basic settings, the dimension filter is gonna be 2D, so we're only gonna mess around with 2D regions, okay? And now we'll click the ellipses, and you will select free 1, and you're gonna hold Control and select free 2, okay? So we're gonna create a region that is composed by these two walls right here. So click OK and click OK. There you go. Now we're going to create the boundaries condition for this this problem. The simulation requires an inlet, an outlet, which we are already messed around. We've already done inlets and outlets many times, but we're also going to use walls for this problem. In CFX, if you any boundary, any face that you don't set up a boundary condition is going to be interpreted as a wall. But this time around, we don't want a default wall condition. We're going to want a free slip condition to these walls, okay? So we're going to create these boundaries as well, all right? And we're also going to create a symmetry plane boundary, because like I said, we're only using half of the geometry here. So we want to create a symmetry plane that is going to mirror everything that is happening in this side to another side, okay? So the regions for these boundaries were defined when the mesh was created, so the names of them are already set. So let's create our inlet first. Let's go here, like we did many times before, click in boundary, and we're gonna name it inlet with the first letter in uppercase, okay? There you go. We already have the inlet selected, which is this wall, okay? And you can already see, remember when I told you guys that this model needs the elements near the walls to be more finer, because we're going to use the SST model, and you can see this right here. Okay, when you look at the geometry from afar, you can see that the elements away from the wall are very coarse, but when you get closer to the wall, to the bottom, they're much finer. Okay, so now let's set up the inlet. Make sure that location selected is inlet. Go to boundary details. Make sure that subsonic is chosen for flow regime, and in mass momentum we're gonna work with normal speed. The normal speed is gonna be 15 meters per second. Just make sure that you have the correct unit right here. We're gonna change the turbulence option to intensity and length scale. We're gonna leave 0.05 for fractional intensity, which is basically the medium intensity. And the eddy length scale, like we said before, is gonna be 0.1 meters. Make sure that the unit is correct. Okay, now click OK. Now let's create our boundary condition. It is a boundary condition, but let's create our outlet condition, which is this one. You click boundary, the name is gonna be outlet. Okay, the location and the boundary type is already set properly, with the outlet being the opposite side of the inlet. So let's go to boundary details. Okay, change the average static pressure to static pressure, and select and set it to 0 Pascal. Okay, and click OK. Now we're gonna create the free slip wall boundaries. So the top and the side surfaces of the rectangular region are gonna be the free slip wall boundaries. Okay, so let me explain a little bit what is a free slip boundary condition. On free slip walls, their shear stress is set to 0 so that the fluid is not retarded. Remember that condition from fluid mechanics where the fluid assumes the velocity of the walls. So we're gonna change this here. This is the default condition, but now we're gonna be working with a free slip boundary condition because we're gonna simulate the external flow. Okay, so on free slip walls, the shear stress set to 0, so the fluid is not retarded. Okay, the velocity normal to the wall is also set to 0, and the velocity parallel to the wall is calculated during the resolution. Okay, so this boundary is an approximation that may not accurately represent the true flow conditions. By using a free slip wall boundary, the flow modeling will be less accurate, but the computational grid size can be reduced by modeling less surroundings. Okay, so this basically allows us to use a smaller domain. And in this case, we're modeling a wind tunnel experiment. So the geometry would match the size and shape of the wind tunnel and use no slip walls. So if this case we're modeling a blunt body, if this case we're modeling a blunt body open to the atmosphere, a much larger domain would be used to minimize the effect of the far field boundary. But because we're using a wind tunnel, this domain can be smaller. And the far field boundary type would be set to be either a free slip wall or a pressure specified entrainment opening if the vehicle, the blunt body, was in open atmosphere, not in a wind tunnel. Okay, so we're going to apply a single boundary to both walls by using the composite region that we created before. Okay, so let's create another boundary condition. This time we're going to name it free walls, and it's already set up to the composite region that we created. Okay, but we're going to change from inlet, the boundary type, from inlet to wall, and we're gonna go here in boundary type, and this is what I was saying about the the default condition. The default condition is that the default condition in nature, where the fluid, as it gets closer and closer to the wall, its velocity starts to slow down until it reaches the velocity of the wall, which is generally 0, especially if you think like the sides of a channel or the walls of pipes. Okay, so we're gonna change the no slip to the free slip condition. Okay, and click OK. And now we're gonna create our symmetry plane condition. So we're gonna create another boundary condition. We're gonna name it sim with y p. Okay, and we're gonna change the boundary type to symmetry, and you can see that this one is selected. Okay, all the walls, all this wall from the, which would be the inside of our wind tunnel. Okay, so but pay attention that we have only selected this part of the wall and not the blunt body face, which we're going to select in after this. Okay, so make sure that you will create both of them. Okay, because if you only create this one, you're not going to be capturing what is happening in here, right? So click OK, and you can see for the first time what the symmetry condition looks like, which is both of these red arrows. One is filled and one is open. Okay, now let's create our second symmetry condition, which is gonna be, we're gonna name it I'm gonna name it, I think it's body that is named, right? Yes. And we're gonna change it to symmetry. Okay, and you can see that it's now selecting the body. All right, go to, actually this is supposed, yeah, this is supposed to be a wall, now that I remember. Okay, because this is not the symmetry, right? This is the blunt body. So the blunt body is, I forgot the word, to hollow izoku. I'm trying to remember. It's a solid object, all right? So this is why we're gonna use the wall condition, but this time is a no slip wall, okay? Because we're not simulating external flow here. This time around, we want the wind that comes closer to the blunt body to slow down and reach the blunt body velocity, which is gonna be 0. Okay, so click OK. The remaining 2D regions, which in this case would just be the bottom face right here, this bottom face, will be assigned the default boundary, which is a no slip wall as well. Okay, so in this case, the name of the default boundary is blunt body default. Although the boundaries body and blunt body default are identical except for the location, the body boundary was created so that during the post-processing, its location can be conveniently distinguished, okay, from other walls. So if we didn't do this last boundary condition, we would not be able to select it, okay, because it would be a generical default boundary condition. Now let's set up our initial values. So we're gonna go here in global initialization, and we're gonna select, instead of Cartesian velocity component automatic, we're gonna change it to automatic with value. And we're gonna have in the X direction 15 meters per second, 0 and 0 for both Y and Z directions. Okay, so click OK. Now let's set up the solver control, the solver conditions. So we go here, solver control. We're gonna change the number of max iterations from 100 to 60. We're gonna change the auto time scale to physical time scale, and I'm gonna set it to 2 seconds. Make sure that the unit is correct, and for the first time, we're gonna be a little more strict to our convergence criteria. Instead of 10 to the minus 4, we're gonna have 10 to the minus 5. So we want a little bit more of accuracy in this solution, okay? So now, instead of stopping when it reaches 10 to the minus 4 in the residual target, it's gonna stop only when it reaches 10 to the minus 5, okay? So click OK. Let's save our simulation. I'm gonna save it as blunt body. All right, and now let's write our input file. So all we need to do is click here in define run. We're gonna leave the name as it is, bluntbody.def. We're gonna save it, and now we're gonna run the solution. Okay. So all we need to do is leave this as it is, and we're gonna start the run. Okay, and now we're gonna see the difference in where that change from 10 to the minus 4 to 10 to the minus 5 comes in place in the solver control. Okay, so before we had the convergence criteria right here, 10 to the minus 4. So when all the curves cross this line, the simulation would stop. Okay, this time this will only happen when they cross this line right here. Okay, so in the previous cases, our simulation would have stopped right now when the last curve crossed 10 to the minus 4. But because we changed this, it's gonna stop only when the green curve, which is the last one, cross this line right here, this threshold of 10 to the minus 5. All right, and we can see this is gonna happen right now. See, we have changed the criteria, and now it only stopped at 10 to the minus 5. Just so you guys know, as a best practice in CFD, we use this value to 10 to the minus 6. So this is the best practice value, so to speak, is 10 to the minus 6 for the RMS residual target. Okay, so this is the first image that I want you guys to send me. Again, the image of your solver, of your simulation converge. Okay, you can print screen this screen. And now let's go to the post-processing. Just check post-process results and shut down CFX Solver Manager and click OK. All right. Now we're gonna see the results in CFD post. So and we're gonna especially want to show you guys how to use the symmetry plane to display the field geometry. Okay, because earlier in this problem we used the symmetry plane boundary because the entire blunt body is symmetrical about a plane. Okay, and due to the symmetry, it was necessary to use only half of the geometry. So however, for visualization purposes, it is helpful to use to see the full blunt body. Okay, and here we're able to recreate this full data set from the half that was originally calculated. Okay, and we're gonna use this this tool is called the instance transform object. Okay, so first we're gonna need to do a little bit of manipulation in our geometry. So we're gonna be able to see what happens when we use the symmetry plane. Okay, so right now we're gonna go to predefined camera and we're gonna select a different view. Now we're gonna select the view from plus X. Okay, so this is the one. You can see the blunt body here, but you know that is tilted from what we want to see. But let's work with this for a while. So let's create our instance transform. Instance transforms are used to visualize the full geometry representation in cases where the simulation took advantage of the symmetry to solve only part of the geometry. So there are three types of transforms that you can use. You can use the rotation, translation, and the reflection mirroring, which is the case that we're gonna be we're gonna use here, the reflection mirroring, okay? So the first thing we're gonna do is click location and then plane. Let me drink a little bit of my coffee. Good. Now we're gonna name it reflection plane, okay? And we're gonna set it up as follows. We're gonna use a ZX plane, and we're gonna leave the Y position 0, okay? In render, we're gonna clear show faces, okay? And we're gonna click apply. So basically, we created a plane and we chose to not show it, okay? If we click here and click apply, you will not be able to see it because we set it up at 0 in the Y position, okay? So let's go back to our predefined camera. Let's uncheck this because we don't need to see it. We're not gonna see it anyway. So this makes the post-processing go faster because he has one last thing to render. And all we did here was create a plane at Y equals 0, which is basically the same location as the symmetry plane that we defined in CFX Pre, okay? So now the instance transform can be created using this plane right here, all right? So from the main menu, let's go to Insert, Instance Transform, okay? You can leave the default name, that's okay. So in the definition we're gonna use is, you're gonna go to instance, sorry, instance info from domain, and we're gonna clear it, okay? Then we're gonna go to apply rotation. We're gonna clear this and go to apply rotation. We're gonna clear it because we're not doing a rotation instance transform, okay? We're also not doing a translation instance transform. We're doing a reflection. We're doing a mirroring instance transform, okay? So you check this option. The method is gonna be from plane, and we're gonna choose the reflection plane, which is the plane that we just created right here, okay? And then we're gonna click apply. All right, now we're gonna use the reflection transform, okay? So you can apply the new transform to the graphics object, okay? For example, you can modify the display of the wireframe as follows. So what we do here is we go here in under user location and plots, we go to wireframe, then we go to view, and then we go to apply instancing transform, okay? Which is here, and we change it from default transform to the one that we created, okay? And you can click apply. And now if you click here in fit view, you can see that we can look at the full body now. This is the one that we created. This is the one that we did everything. We created the boundaries, we created everything for it. This one right here. And this is the symmetry view. It's the mirrored image of it, and that we can use here to see the full geometry, okay? And you can see the full wind tunnel, and you can also see the full blunt body right here, okay? So now let's work with our full geometry. Let's see what's going on right here. So let's create some velocity vectors, okay? We're going to create a plot to show velocity vectors behind the blunt body, okay? So the first thing we're going to need to do is create an object to act as the locator, which in this case will be a sampling plane, okay? And then we're going to create the vector plot itself, all right? So let's create the sampling plane. First, let's define, let's preset our camera a little bit better. So instead of using the plus X, we're gonna use the plus Y. All right. So this is gonna ensure that the changes that we do here can be seen. So let's create a new plane. Let's go here to location, plane. The name of this plane is gonna be sample. All right. And its characteristics are gonna be the following. The method is gonna be point and normal, so we're gonna set up a point and a normal for this plane, for the creation of this plane, and the characteristics are 6 minus 0.001 and 1 for the point, and for the normal we're gonna use 0, 1 and 0. Okay, now in plane bounds we're gonna select rectangular. Okay, the X size is gonna be 2.5. Where's my point? Here's my point. 2.5 meters. The Y size is also gonna be 2.5. And the plane type, we're gonna choose samples. So we're gonna want 20 samples from each direction. Okay. In the render, we're also gonna clear show faces, and we want to see the lines. So we're gonna see, we want to check the show mesh lines. Okay. And then you can click apply. So there is our domain. Okay. Sorry, not domain. There is our sampling plane. Okay. Yeah, you can also zoom in to see that the location of the sampling points where the lines intersect. Okay, so this is where what you see here is where the lines are intersecting. There are a total of 400 sampling points, which is basically 20 by 20 when you look at the samples here. So it's 20 by 20. And a vector can be created at each of these sampling points. Okay, so turn off the visibility for this plane here, because this is only gonna be used to create the velocity vector plane. Okay, so we don't need to see the sampling point, we need to see the velocity vectors. Okay, so let's create a vector plot using different sampling methods. Okay, so let's create the vectors. You can go here, sorry, not here, here, right to the right of location, which is vector. Okay, you can leave the default name, this is not a problem. And now we're gonna I'm gonna show you different ways to create a vector plot. Okay, so in the geometry we're gonna select sample. Okay, the sampling method for this first case we're gonna use vertex. Okay, and you're gonna go to symbol, and you're gonna change the symbol size to 1 to 0.25. There you go. You can see that the vector. Oh, by the way, what I did here is just I clicked in the magnifying case with a plus on it, the zoom box, and I did this, so I can see the vectors plots, the vector directions interacting with the blunt body. So we know that the wind is coming from the right to the left, and this is how it's interacting with the blunt body. And you can see here that the wind changes direction in this region right after the blunt body. Okay, so these are the first two images that I want from you guys. I want this image right here with the velocity vectors and the blunt body in view. So what you want to do here is you don't want to print screen. Remember, I showed you guys how to do this. You go to save picture. You can use the PNG or JPEG, doesn't matter, but I want you guys to change the scale. So I want you guys to use a 500 scale so the picture is better. And also I want you guys to change the wireframe line width from 1 to 5. Okay, so this is better, can be better seen. All right, so this is the first picture, and the second one I want a zoomed in view of where you see the recirculation happening in the wind. Okay, so I want this image as well. So we want two images from here, this one and this one. Okay, so now let's change how we see these vectors. Okay, what you want to do here is you're gonna go back to the vector, you're gonna change sampling from vertex to equally spaced, and you want to see 1,000 points instead of 100. Okay, and then you're gonna click apply. So there you go. Now you have much more vectors in our image. And again, I want this image from you guys and this image here. Okay, and you can see that this way of seeing the vectors has given us way more points to see, and you can actually change this. If we use the default one, you can see that is way less points. We only have 100 points here, but we want, let's say you can choose 500. This is much closer to the vertex style that we've seen before. But if you want even more points, like we did, and we see a lot more points, and you can actually see how it improves the visibility in the recirculation region, because we can clearly see two recirculation patterns, one that goes counterclockwise and is larger, and one is a little bit smaller one. It's almost like it's squished and is going in the clockwise direction. Okay, so another two images from you guys here. One that I can see that you can see the full blunt body, and one that you can see both the recirculating zones. Okay, so you already have 4 images to send me. Okay, now let's ignore the vertices on the sampling plane and let's increase the density. Sorry, this is what we did. Now let's change the location of the vector plot by applying the following settings. Okay, so instead of using the sample plane as a location, we're going to use our symmetry plane. Okay, and click apply, and there you go. Now the sampling plane is the one in the middle. Okay, so if you set it up in the proper view camera, you can see the whole face and the whole velocity vectors inside the wind tunnel, and all the way from the inlet reaching the blunt body and going around it all the way to the outlet. Okay, so to better see this, I want you guys to change your legend. Okay, so from vertical, change it to horizontal. Okay, also I wanted you guys to do something else. Instead of using the line arrow, you're gonna use just the arrow head. Okay, and you can see that it's very small. All right, so I want you guys to also normalize the symbols. Okay, and change it, not 4 to 1. There you go. I want you guys to send me this image right here. So all we see here are the arrowheads, and we increase its size so we can see how it performs. Okay, so I want you guys to send me this image. I want an image from behind the blunt body, and then you can also change the legend to be shown at the bottom. There you go. And then I want to actually, instead of an image from behind and an image from the front, I want an image that shows me the blunt body in zoom. Okay, so what I want from you guys is this image with the wind channel full in view, and I also want an image zoomed in the blunt body, so I can see what is happening behind the blunt body and in the front of the blunt body. Okay, in the front of our vehicle. Okay, now we have 2 more images. I want to see the pressure distribution on the symmetry plane. Okay, so let's set it up, right? Go to the boundary named body, which is this one. Okay, you don't need to create a new symmetry plane. You can also see which one this is. This is this body right here, okay? So let's change from constant to variable, and we're gonna go also to view, and we're gonna apply an instance transform in instance transform 1, and again is gonna be a reflection mirroring transform, okay? And we can click apply. And also let's clear the vectors, and here you can see the pressure distribution around the blunt body, okay? So you'll be able to see that the pressure here is negative, okay? No, sorry, not negative. The whole pressure here is negative, but the pressure here is larger than, for example, here in the front, right? Because the wind is coming from this side, okay? So now let's do one more thing here. Let's go to the sim P, and let's go to render, clear show faces, and ask to show you the mesh lines, okay? And there you go, you can see the mesh lines from the symmetry plane in the bottom, so it doesn't occlude our view from above. And you can see that the closer that the mesh gets to the blunt body, the finer it gets, and the closer it gets to the wall, we have even a special type of mesh here, which is what we call the inflation, which is a very organized way of doing meshes, okay? We put this one. Now let's create a surface streamline to display the path of air alongside the surface of the body, okay? So let's clear this plane, and let's clear, not plane, let's clear this boundary and the other boundary, okay? So in order to show the path of air along the surface of the blunt body, we can create surface streamlines as follows, okay? So we make sure you have the visibility turned off for this, all the things that we have created here, and let's create a new plane, okay? So we go to location, plane, we're gonna name this plane starter, okay? So this is the plane that's gonna be the starting point for the streamlines, okay? Change the method from XY to YZ and select the X position to be minus 0.1 meter, okay? And click apply. So we can see, oops, that's not what I wanted, I want this one. You can see that we created a plane right here, okay? Don't be frightened that the plane is only showing here. It's only showing here because we're not doing stance transforming, and because we don't need to, because we don't want to see this plane in our symmetry, okay? We only want to see the streamlines that we're going to create from this plane in all the body, okay? So this can be left as it is, all right? Now, after this, let's change the view to the isometric view Z up, so we can see the full body properly. And also let's turn off the visibility for this plane, because like I said, we don't want to see this plane. We want to see the streamlines that we're going to create from this plane. So to create streamlines, you can go here, streamline, the default name is fine, and we're going to configure as follows, okay? The type is going to be surface, because we're going to create it from a surface, from a plane, and not from a 3D place. The surface is going to be the surface streamline. Sorry, I was looking for the surface streamline. The definition is going to be the body, okay, which is, if you don't remember, the body is the blunt body, down there is our vehicle, okay, and where it's going to start from? It's going to start from our starter plane, okay, so we're going to start from a location. We're going to choose the location that's going to start from, and it is the starter plane that we just created, which is this plane right here. So the streamlines are going to start from there, they're going to come from there, okay. So let's change it. The max point, we're going to want to see more, we want to see more than 25, and the direction, we want to see only the streamlines that are going forward, so only the streamlines that are in the positive x-axis, okay. So you can click apply. There you go. We can see the streamlines going over the blunt body, but we also want to see them in our instance transform, okay. So we create the instance transform for reflection and mirroring in the view. Remember to change here to instance transform 1, and you can see it in both, in the full body, okay. So this is another image that I want you guys to send me, okay, the streamlines for the full body, okay. So what we want to do right now is I want to show you guys that you can move the position of your objects very easily. For example, let's say you just want to see how it looks, okay. So what you want to do, usually you're in this form of the arrow, right? So what you want to do is you want to click here in select, and you're going to change it to single select, okay. Now you can change the position of the starter plane, and you can see how it affects the streamline. See? So I want you guys to send me an image from whatever you want to place this plane right here. So you can place it like here, or you can place it down there. Just don't place it here, because then you won't have many streamlines to see, okay. Place it before. You can place it in the middle of the blunt body or before it, okay. So find a good place to see the streamlines, and I want you guys to send me an image like this with the plane visible, so I can see where you put your plane, and also the streamlines, okay. So this is basically it for this tutorial, for this problem, okay. I hope you guys have enjoyed it. If you have any questions, let me know by email, and see you guys next lecture, okay.